Good afternoon, everybody. Thanks for being here today. I know it's not easy to be on the afternoon of the last day of a conference because, many of you have to fly, many of you have to come back and so on. And, doesn't feel like coming to a talk, okay? So I appreciate very much that you take your time to be here. I'm Roma, co-founder, scientific director of Multiverse, also professor of theoretical physics. So here I'm not gonna be giving you a technical talk about quantum algorithms. I could spend all the afternoon giving you all the technicalities about the things that we do at Multiverse, okay? But instead of that, in this talk, I want to talk about business, all right? I want to talk about actual business applications, how to make quantum computers useful, okay? The quantum computers that we have already nowadays, and in which use cases, in industry, we are finding actually value, okay? So, in Multiverse, we do quantum software, okay? For many different industries and for different, business verticals. We're actually seeing that, these NISQ quantum processors that we have today, they start to be useful for some specific applications. We think that, well, we have seen, and you will see in this talk, that one can already start to extract business value out of these machines, in a little bit along the lines of what John Preskill was saying yesterday, that these NISQ machines, they should be useful for something. That's also our philosophy. Obviously, fault tolerance is something that is very important for us, but it's even more important for us to find value of the machines that we have today, okay, in business. And that's actually the goal of this talk. So hopefully, by the end of my talk, I will have convinced you that this is possible, okay, in several applications. So I want to start explaining what this talk is not about. As I was saying before, this talk is not about, telling you many equations and lots of technical details about our algorithms. I can be as specific as you like afterwards if you want to know details about how we actually do things, how we actually implement our algorithms, how we make things work. I can give you all the details you like, okay, but not in this talk, okay? So this talk is not about equations. It's also not about quantum advantage understood as quantum supremacy. So here my goal is not to think or to try to benchmark when quantum computers are going to be able to solve problems in such a way that no classical computer will ever be able to solve them, okay? In this talk, I'm not going to be focusing on that. That's not our target from a business point of view. It may be a target from an academic point of view, and it's perfectly legit, and that's important. But from a business point of view, the target is different, okay? I'm also not going to explain you anything about fault tolerance because we are going to, we want to work with the quantum computers that we have today. They are small, they are noisy, they are imperfect, and so on. And we want to use these imperfect machines to actually do something useful, okay? This talk is about bringing business value, okay, with the machines that we already have today. This is something that we call quantum business advantage. It's about doing something that is useful for the people in industries, okay? For the people in industries, in business, you have to be able to provide solutions that are already better than the internal solutions that they are using, that they find it useful and they want to put this into production for whatever reason, okay? Because in business, they may have many reasons to actually put a solution, okay, into production now. So, obviously, it will be great once we have fault tolerance, once we have quantum computers fully developed. Once we have that, we are going to be able to solve everything. Now, the hard question is with the machines that we have today, that they are imperfect, they are noisy, and so on, what can we do that is useful, all right? I mean, that's the hard question to answer because one will be tempted to say, until these machines are actually more powerful, we cannot do anything that is actually practical, okay? What I want to show you today is that this is not true, okay? That you can actually find applications. If you target very specific applications and algorithms, okay, you can start to find business value of quantum computers as they are developed today, even though they are small and noisy, okay? So let me explain you and show you this by presenting a series of benchmarks, okay, that we have obtained with clients in projects, okay, in different verticals, okay. I'm going to be talking about clients in finance and also clients in manufacturing. All the data, all the problems that you're going to see here, these are not academic or toy models, okay? These are real data, real problems in very dirty and complex environments, okay? Where we actually had to do a lot of reverse engineering to actually be able to put all this into a quantum computer, okay? Run a quantum algorithm, or perhaps a quantum-inspired algorithm, or perhaps a hybrid solution, and show that this solution was actually better than what the people were actually doing, and the best classical solution to the best of our resources, okay? This is a first example. It's about portfolio optimization in finance. Portfolio optimization is the canonical problem In finance, you want to maximize the returns and minimize the risk of a series of assets, and should you be investing and disinvesting in these assets over a period of time, and so on. Now, this problem is extremely hard, as you probably know, and solvers that are classical nowadays, they are really having a very hard time in order to not to get stuck into actual, local minima and solutions that are non-optimal. Okay, so at Multiverse, we've been running a series of projects on this with different financial institutions. We've been working with BBVA, which is a bank in Spain, with CaixaBank, which is another bank in Spain. We've also been running our own internal checks. And nowadays, we have a portfolio optimization algorithm, which is hybrid, okay, which combines classical and quantum processing that is actually able to match the best solutions in the market, okay, and is actually able to beat them in some very complex scenarios. So actually, not only are we finding the best portfolios, okay, but we're actually beating the industry standard, okay, which is an optimizer that is called Q2B. This is what people such as other asset management companies they are using. So we're actually able to solve much larger portfolios than with the standard optimizer, okay, in a fraction of time, okay, than the standard classical optimizer. This is a tool, okay, that is extremely powerful, all right? And we are putting that into production in a couple of financial institutions already. Next, I want to talk about another financial application. This is about Forex trading, okay? This is about trading in a market, in the currency market, okay? This was a project that was done with a large petrochemical company. It's gonna be out in the next weeks. And it was, again, with real data. The problem that they had is that, well, they had to optimize their strategy for investing and trading in this market, okay, over a period of time. They had some machine learning algorithm that told them the decisions whether in what to invest at what time, okay. This is the typical machine learning problem, okay, that you have to decide if you invest or you not invest in what at every point in time, no? So what we did was, a quantum algorithm. In this case, it was a quantum machine learning algorithm, also trained with all this real data that they gave us, with a lot of, back testing and so on. At the end of the day, we were able to produce a solution that was actually better, not just better than what they had inside the house, but actually better than the best machine learning solution that they could produce. Okay, actually, at the end of the day, when you are talking with a company, you have to translate this into dollars or euros, okay? This is the measure that they understand, right? And it was easy to convince them because we showed them that in a 1 year period, we were actually producing 1 million more euros than with the strategy that they were using before. This project was also very successful, and now it's also gonna go into production in January. Good, this is a different example. It's with Bosch. On manufacturing. This was a problem about artificial vision. This was a problem about detecting defects in the manufactured pieces in the factories of Bosch, okay, by using machine learning vision, okay. They had pictures of the pieces that they were producing, and from these pictures, one had to be able to detect anomalies, okay, that correspond to the actual imperfections in whatever they were fabricating. This is, again, the canonical machine learning problem, being able to detect defects and anomalies in a set of data. In this case, it was on pictures, okay? We did it, in this case, using quantum-inspired technology, okay, which is a classical technology that, mimics the way in which a quantum computer is processing correlations. We are also very good at that in Multiverse. And, well, we were able to improve the precision of the detection of the defects, okay? But not just improve the precision of the detection of the defects, but also compared to the best deep learning, machine learning solution that we were able to produce in coordination also with them. It was much more efficient in memory, actually a factor of 5. Now, this is very important because first it was a quantum-inspired solution, okay? So it means you don't have to connect to any quantum computer on the cloud. It's running classical computation, okay? But it's quantum-inspired, and it takes remarkably little memory, okay? So, this is one of those applications that you can actually run on the edge, okay? So, imagine that you want to put an image recognition system on a satellite, all right? So on a satellite, you cannot put a quantum computer on a satellite, okay? You need something that runs there, okay? And memory is also a limited resource if you are running on a satellite. So this is the kind of algorithm, okay, that you could throw there. Okay, Also, more artificial vision, but this time quantum. This was with Ikerlan. Ikerlan is a manufacturing company in Spain. They came as, again, with a very similar problem to Bosch. They wanted to detect fractures in wheels. Okay, they were manufacturing wheels. You know, from time to time there is a fracture because of imperfections in the process, and you had to be able to detect that. No, the way to detect it again was with image processing. They were taking pictures of everything, and they were processed with a artificial vision algorithm in order to be able to detect these fractures. Okay, now what we did with Ikerlan was a quantum algorithm, again a quantum machine learning algorithm that was able to detect fractures in these wheels, okay, in these manufactured pieces. And we were improving the performance with respect to the solution that they had, and then we also compared to the best solution with the same data set that was provided by Amazon AWS, okay? And we matched the precision of AWS, but turned out that our solution was 24 times faster, okay? This was a quantum algorithm, again, running with real data, and this is gonna go also into production very soon. Now, more about manufacturing. ZF is a German company that actually produces pieces for cars, okay? So if you have a car, inside of your car, probably there is some piece that is being manufactured by these guys because they are everywhere, okay? In this case, this was an optimization problem, okay? It was an optimization problem about how to optimize the configuration of some clutches, okay? This is a, this is a very interesting problem. Actually, you have to find the optimal configuration of a series of disks, okay? How to arrange the clutch, and when you put it mathematically, it turns out that is again a very complicated optimization problem, one of those intractable NP-hard problems that it looks like how the hell are we going to be able to solve this, okay? They had some internal optimizer, again, they were pretty limited as to what they were able to solve. Using classical optimizers, also like Q2B, Palisade, and other solutions, it was also very limited the kind of problems that we were able actually to tackle. And in our case, again, using quantum computing, we were able to solve problems that were orders of magnitude larger in problem size, okay, with respect to what they were able to solve. Not just that, but also much, much faster. As you can see, for the largest size that they could handle with their classical solution, we were actually 1,000 times faster, but we could go much beyond in size, okay? By the way, I'm not mentioning this, but I mean on these slides you can see that many of these things that I'm talking about, you can find them on papers on the archive. Okay, so they are in the process of being published. Okay, so if you're interested about the actual equations, technical details, platforms and so on, feel free to have a look, or just come later and I will be very happy to give you more details. Okay. Good. Let's come back to finance with Credit Agricole Corporate and Investment Banking. They came to us also with a problem on pricing of options. This is a very hard problem in finance, okay? And they were using deep learning to solve this problem, okay? There are some very complicated stochastic equations, and at the end of the day, they were using deep learning, okay? Here we proposed a quantum-inspired solution that was improving neural networks, okay? By using, a technology that is called tensor networks, we improved a lot the precision, we improved a lot the memory performance, okay, and also the training time. In fact, it was 3 times faster than the best solution that Kasib was able to produce, okay, internally, and not just faster, but also 3 times more efficient in memory, okay. So, this was a great thing for them because we were able not just to replicate what they were obtaining, but actually to improve, the precision and actually doing it much faster, okay. Now, for a bank, this is very important because this is the type of things that they have to do very intensively, okay. So if you save, memory and also time to them, this is also extremely useful for them. Okay. Ally, the former bank of General Motors, they were interested in an index tracking problem, okay? Now, this is the problem of replicating the behavior of an index, let's say the NASDAQ 100, but instead of using 100 assets, let's use 25, all right? So if you go to your bank and you say, hey, I want to buy one of these index tracking things, these are typically called ETFs, okay? This is a financial product that you can go and buy, okay, if you are into these investment stories, no? And this is a very complicated optimization problem. How the hell are you going to replicate the behavior of an index of 100 assets with just 25, okay? It's an approximation problem. You have to minimize the distance between what you are building and the actual index, no? When you put this down into equations, again, this is one of those intractable problems that are very hard, and using quantum computing, in this case, we were able to produce an index tracking algorithm that was not just replicating the index, but actually providing better returns, okay, and lower risk. So there is something in finance that is called the Sharpe ratio. That is the ratio between the return and the risk, and this thing has to be very high for a product to be very good. It means that you have a lot of return and very low risk, okay? And in our solution, we are actually obtaining extremely large Sharpe ratio as compared to, the typical solution. Okay, last but not least, again with Credit Agricole, with CASIP, this was a problem called the Fallen Angels. It's a credit scoring problem. It was the typical machine learning problem where you have to decide whether a given bond is going to be downgraded in a very short time. Okay, they have to be able to predict this in advance in order to, do something with that. Okay, it's a machine learning problem. They had an internal solution based on machine learning algorithms. We were able, using quantum computing, we were able to reduce the memory consumption, also increase the accuracy, okay, by a large factor, and this is also going to go beyond. Okay, they were very happy about this, and it's going to go into production. Okay, I could spend here the whole day, but I think it's better if I just stop here. I can give you as many details as you want. Okay, as I said, there are also, I think all of these examples except for one, there are papers on the archive that we have posted where you can find all the technical details also, but I'm also available for questions if you like. Thank you.
Okay, we have time for questions. Yes.
Hey, Oscar.
Hi, Roman. First, congratulations. I'm glad to see you're able to deliver already a ton of value with the things that you're doing. My question is, because I see that sometimes you've used quantum-inspired machine learning methods, sometimes quantum, or purely quantum, or kind of like a machine learning method that leverages a quantum computer. I was trying to understand if you had used your quantum-inspired for everything, would that be enough, or would that already provide?
I don't think so. No, depending on what we have learned at Multiverse is that depending on the application, sometimes the client comes to you and tells you, hey, I want to use quantum-inspired. Okay, you do quantum-inspired. Okay. But what we have learned at Multiverse also is that depending on the application, it's better to use one algorithm or other, okay, and also better to use quantum-inspired or quantum, okay. Now, in this case, it was mostly the client who was telling us, hey, I want to use some quantum-inspired solution just to see how things are going, or some others who really wanted to test the quantum technology, and they really wanted to go for quantum, yeah.
My only thing, maybe just, and then I'll pause, is just I want to understand, because in general, if you could do this, already provide results with mostly running something on a classical computer, probably potentially be cheaper.
There are instances, for instance, for optimization. Okay, for optimization, it depends on the optimization algorithm that you use. Okay, and depends on the actual instance of the problem. Sometimes it's better to use quantum or quantum-inspired. So it's not that you can just replicate everything. Yeah, there is an overhead. Yeah.
Thank you.
Okay.
Any more questions from the audience? Yes.
Hey, Roman, how's it going?
Hey.
So I know that you said no math, but I want to try to break that rule a little bit. What does quantum-inspired mean here?
For us, it means tensor networks. Does it tell you? Does it solve?
No, yeah.
Okay.
So it's tensor network-based method.
Yeah, we were using tensor networks. Yeah. Tensor networks.
And tensor networks have been around for a while. So the quantum part, is there something additional that you're putting from lessons from quantum computing, or is it more just
on tensor networks? Yeah. Well, everything that I was showing here is optimization problems and machine learning. Okay. For optimization problems, you know that in tensor networks we have a lot of variety of optimization algorithms, and we were tailoring them to the actual problem because these are classical problems. Okay, and then you can do many tricks to actually improve the efficiency. Okay, and for machine learning, these are training a tensor network to actually be able to recognize patterns. Thing number one, or perhaps improving the performance of deep learning, okay, using tensor networks. When you do, and here I'm going a little bit technical, when you see a deep learning structure, you have layers of neurons, okay, and in the middle you have these transfer operators that are super huge in terms of memory. You can decompose that with tensor networks and improve the accuracy. Yeah.